Hi everyone, this is Lauren, and today I'm going to share with you my visualization tools I made for stereographic projection. So the reason I wanted to do this is because when I was studying for my test, then I realized how important it is to be able to visualize what's going on inside of the unit cell with the different direction vectors in the North Pole in order to really understand where the wolf net comes from and how to plot points on a wolf net. As a quick reminder, stereographic projection is a method we use to represent 3D crystallographic information on a 2D plane. For example, on this diagram to the right, you can see each of these directions on the left plotted with information about the types of symmetries in this crystal. The first thing we'll have to define is the North Pole. The North Pole tells you which direction is facing up in the unit cell. The North Pole vector is going to be the direction that we're viewing the cell from. So as you can see in this example, the North Pole vector is set to be 1, 1, 1, and this is what it looks like from that direction. With this tool, what you can do is you can move around the North Pole and then see what the new cell is going to look like. The easiest North Poles to use are going to be the 100, 110, and 111 families. This is because they involve the simplest transformations and will usually look pretty symmetric around those points. Now that we know how to plot the origin of the wolf net, we can move on to plotting other points. To project a direction onto a wolf net, what you do is you take your direction from the origin to this point out here, and then you draw a line from the point to the South Pole, and you look at where it intercepts with this plane. So the first value we'll need to calculate is phi. Phi is defined as the angle between the North Pole vector and your chosen direction. What you should notice here is that as phi increases, so does the distance from the point on the wolf net to the origin. The next value we'll need to know is theta. So to find theta, what you do is you calculate the angle between your vector and the 100 vector, which will be set as the rightmost point on the wolf net. What you can see is that as I'm moving around theta, this second vector is going to be moving around the North Pole. Another thing you can see is that you can set theta from any direction you want. So for here you can choose 0, 1, 0, negative 1, 0, 0, 0, negative 1, 0. But on a wolf net, it all looks the same. The only thing that changes is which directions are set as the right, left, top, and bottom sides of the wolf net. Now what we're interested in is how these directions look inside of a unit cell on the wolf net. So here what I have is the same demonstration where you can move around theta and phi, and then see what the resulting point on the wolf net looks like. To add on to this demonstration, what I'm going to do is move around the North Pole vector. So from here you can do the same thing where you can adjust theta and phi, and then you can look at the new directions and see how it compares to the original one. I also made a more interactive version of this where you can click on any point in the wolf net and then see what the resulting vector looks like inside of the unit cell. One thing you'll notice as you continue plotting different directions onto the wolf net is that various types of patterns will start popping up depending on which families you're looking at. Here I've shown the 100, 110, and 111 families plotted in the northern and southern hemispheres, which is represented by red dots and blue circles. So this is what the different families look like. The next thing we're going to do is change the lattice parameters of the unit cell. This doesn't really change that much when we're looking at the North Pole vector, but it will affect the other directions that project into the wolf net. So So right now I'm changing the North Pole direction without changing the lattice constants. And you can see once I start adjusting the lattice constants, that starts stretching the other directions. A useful way to see how the lattice parameters affect the directions is by taking the same vector that has the same Miller indices and then adjusting the lattice parameter and seeing how it is transformed. So what I'm doing here is I'm taking one vector and I'm moving around one of the lattice parameters. So you can see this one's moving it kind of up and down. That one doesn't really affect it. For this vector again, this direction doesn't affect it that much. This one's kind of moving it back and forth, and this one's squishing it towards the center. The thing to remember here is that even though the Miller indices aren't changing, the Cartesian coordinates of this vector will actually be changing. This is shown by the text box in the corner of this diagram. Now for the final part of this demonstration, what I wanted to do was I wanted to look at the same families of vectors that I was looking at before, and then I wanted to see how those were affected by the lattice parameters A, B, and C when projected onto a wolf net. So what I found was that moving A kind of squished them inwards towards the vertical axis, and moving B did the same but horizontally. Finally, moving C moved the inner points outwards towards the circumference of the wolf net. Another interesting thing to point out is that no matter how C, the points on the farthest right, left, top, bottom, and middle will stay the same because those are the points you're using to define all the other vectors from. Okay, so that's it for my project. I hope you enjoyed it. And thank you to all of our teaching instructors and staff for making this semester great.